In this R tutorial, we'll learn how to evaluate whether there's evidence of disparate or adverse impact using the z-test and the z-impact ratio test. And so we are already in RStudio, so let's get started by going to File, New File, and RScript to open up an RScript editor window here. Okay, I'm going to paste in some general information here to get us started. Again, the focus of this R tutorial is on how to evaluate disparate impact, which is sometimes called adverse impact, and we'll do so using the z-test and the z-impact ratio test. I also have another tutorial that focuses on how to evaluate whether there's evidence of disparate or adverse impact. And in that tutorial, I focus on how to apply the 4/5 rule, which is also called the 80% rule, as well as how to apply the chi-square test of independence with and without the Yates continuity correction, as well as the Fisher exact test. Now, I won't get into the details here about when you might use certain tests, and it's particularly what type of statistical test to pair potentially with the 4/5 rule test that the US government recommends via the Uniform Guidelines and the EEOC, the Equal Employment Opportunity Commission. But here are some readings where you can learn more about these different types of tests and how well they perform in smaller versus larger samples and the impacts on false positives, false negatives, or in other words, type 1 and type 2 errors. And so I'll scroll slowly here so you can take a look at these different references I provided here. All right, so the first thing that we're going to do to get started here before we get into actually estimating the z-test is to set our working directory. And I'm going to use the setwd function from base R to do this. And so I'll do setwd, and within the parentheses, quotation marks, and within those, I know that the folder where the data file that I'm going to use for this tutorial lives in my H drive, H:/ and R workshop folder within that drive. Okay, I'm going to click run here to run that line of script. As you can see down here in my console, I get blue text, which usually is a good thing. And also you'll see this verified in my console window here at the top that the H drive R workshop folder has been set there. Alternatively, you could go to Sessions, Set Working Directory, and Choose Directory to do this through drop-down menus and to manually select the folder where you are storing the data file. Okay, and so this will almost certainly differ from the folder and the path directory that I have here. All right, the next thing that we're going to do is let's read in the data that I've mentioned, and I'm going to be using a function called the read_CSV function from the reader package. And because I'm using the reader package, I need to make sure that first it's installed by using the install.packages function from R, from base R, and within the parentheses and within quotation marks as the sole parenthetical argument, I'm going to enter the name of the reader package, which is READR, all lowercase. Now, I could run this, but I have very recently installed the reader package, and so to save time, I'm not going to update that package by running this line of code. If you need to install the reader package for the first time, or you haven't updated it recently, then I recommend running this script here, running this code right here. I'm just going to annotate this out here by putting a hashtag in front of it so that it won't run as part of our overall script here, because I don't need to do that step. What you will need to do most likely if you've started a new session, even if you have the install.packages, or even if you have the reader package installed already, is you'll need to use the library function. And within the parentheses here, type in the name of that reader package there. Remember, R is case and space sensitive, so it's READR, all lowercase, and click run. We see down here that we can now access that package and the functions within that package. Again, why are we doing this? Well, I'm going to use the read_CSV function here to read in the data file for this tutorial. Now, in terms of what I want to call this data frame object that I'm going to read in using the data file, I'm going to call this just df. That's my way of just brief annotation that's fairly conventional for data frame. And I'm using the left-handed arrow so that I can assign the data file data to this data frame object here that I can subsequently reference. Okay, so to the right of the left-handed arrow, I'm going to type in read_CSV. And as the exact name of the file is disparateimpact.csv, or at least that's the name of the file that I'm working with today. And that goes within the quotation marks, and it's R is case and space sensitive with titles. File names, and so you'll see that the D is capitalized, the I is capitalized, there's no space between disparate and impact, and make sure you have the .csv extension if you're using a .csv file, which is what we use with the read_CSV function there. So I'll click run to run that line of script there. Now, you don't need to use this particular function from this package to read in the data. You could just as easily have done this copy that line and paste it here. And you could change that underscore to a period or a full stop, and you'd have read.csv. And now we're talking about a function that comes from base R, which means you don't need a specific package. So this would work just as well too. If you don't want to install the reader package, you could just run this line right here. Okay. All right, I'm going to annotate this out though, because I've already run this line of script here to read in the data frame object that I'm calling df. Let's go to our global environment here, take a look at that object. As you can see here, it tells us there's 274 observations. That's the number of cases we have, and there's 3 variables. And we can see that here. In this data set, let's assume that every row represents a unique applicant. And here is their unique applicant identifier number, ranging from 1 to 274. Very convenient there. Now, the next variable over, the next field over, is the cognitive underscore test variable. This is a cognitive ability test. Let's assume that this company is using with its applicants as a selection tool or a hiring tool. And we just have here a binary or dichotomous. Either you pass this test, or if you go down lower here, or you fail this test. There's 2 levels to this categorical variable here. And then we have our gender variable here. Okay, this is our protected class variable that we're going to be working with in this demonstration and tutorial. And in here, let's assume that this is self-reported gender by the applicants. And so we have man as the 2 levels here and woman. Okay. And so both of these variables here that we're going to be working with, cognitive underscore test and gender, are both categorical or nominal in terms of their measurement scales. And because they do not have inherent numeric values, and they have 2 different levels within them. So we're going to be ultimately creating what's called a 2x2 contingency or cross-tabulation table to summarize these data and to begin working with those data so that we can estimate the Z test as well as the Z impact ratio test. So let's move on to that next step now. So as a first step, I'm just going to make some annotations here and indent this a bit to indicate that we're going to do the Z test first. This is sometimes called the Z difference test. So you'll see, and I use the underscore here to represent a subscript. So Z underscore D would be Z subscript D for difference. So Z for difference. So sometimes this is called a Z difference test as well, and you'll see why in a little bit. Okay, so what's the first thing that we need to do? Well, as I mentioned, we need to create a contingency table, which is also called a cross-tabulation table. And the way that we're going to do this is there's different ways that you can create tables in R. I'm going to use the cross-tabs, the X tabs function from base R. So you don't need a special package for this. This is a function that comes standard in base R. So when you download R, this is already available. Within the parentheses, the first argument for this X tabs function is we're going to specify the table or the contingency table, which we'll use the tilde. We start with the tilde, and then to the right of the tilde, and it doesn't matter if you have spaces or not here, to the right of the tilde, we're going to put first our gender variable, which is our protected class variable, plus our selection tool or selection test or hiring test variable, which is our cognitive underscore test variable. And so where did I get those names? Well, if you run the names function down here in your console, I'm just doing this so it doesn't save as part of our formal script up here, and I put in the name of our data frame, which is just df lowercase, and I hit return or enter, I can get my exact variable names here. So I could have just copied and pasted these like I'm doing here. So copy and paste. Okay, so this is specifying the what is going to be in our contingency table in terms of the variables. And so what's the next step? The second argument in this xtabs function is going to be data equals, and this is where you specify the data frame. And this is the data frame where both of these variables come from. Okay, and we can see here, we know that df is our data frame and both of these variables live here. And so we're just going to enter data equals df. Okay, if we were to run this just by itself, we'd see down here in our console, we print in our console a contingency table or cross tabulation. And so here you can see the rows represent men and women that are in this sample of applicants who participated in this cognitive ability test here. And then the columns are whether they failed or passed that cognitive ability test. And so you can see, for example, we have 70 men here who passed that cognitive ability test and 90 failed. 42 women passed it and 72 failed here. So these are the data we're going to be working with. Now, we're going to use the left-handed arrow operator here to assign this contingency table to an object that we can subsequently reference. You can call it whatever you want. Anything to the left arrow, you can pretty much name what you want. Just make sure that it starts with a letter here, okay? And so here we have observed. All lowercase is just going to represent our observed frequencies or observed counts as part of this contingency table, because this is all this represents is just the raw counts of how many people passed, failed by the other category there. So we're just going to rerun this now. Rerun that line of script or code there. And now you'll see we have an object here that is a table object that has values here, and you can see this represented over here in our global environment. So we're adding another object here, and again, this is so we can subsequently reference it. Okay, so the next thing that we're going to do is we're going to create objects, and this is so that we can create some objects that we can also reference when actually computing the z-test itself and the z-score. Okay, so we're going to create objects for the total number of applicants by gender, okay? So we're going to create, well, how many men in total, for example, participate in the cognitive ability test? So we're just going to be adding up behind the scenes how many failed, how many passed, and that's going to give us the total number of men. So we're estimating the row marginal here, or the total number of men. We're doing the same thing for women too. So that's what we're creating here. We're going to create two objects. The first I'm going to call capital N underscore men, and this is where N represents the sample size specifically, and as that's a fairly common naming convention here. And I'm going to put the left-handed arrow next, because to the right of this arrow, I want to decide what I'm going to use to assign that value, which is going to end up being the total number of male applicants or men applicants, to this object that I'm arbitrarily calling N underscore men here, okay? And so the way I'm going to do this is I'm going to use matrix notation. So bear with me for a second here, and I'll show you how this works. Well, we're going to use first the sum function that comes from base R, just sum all lowercase, type in our parentheses there. Now within that sum function, as the sole parenthetical argument, we're going to type in observed. This should look familiar. This is the name of this contingency table object we just created there. So we're now referencing this object. Now we're going to right immediately after that observed contingency table object, we're going to add brackets, okay? Not parentheses, but brackets there, okay? And now we're going to use matrix notation to sum up this row right here. We want these two values. We want to take the sum of, in this case, it's 90 plus 70, the total number of men who failed and the total number who passed. This gives us the total number of men in our sample here. And so how do we do that? Well, with matrix notation, the row number comes before the comma and the column number comes after the comma, okay? And so if we put before the comma a row number here, we're saying, and we don't put anything after the comma in terms of a column number, we're saying grab this whole row here, reference this whole row, okay? And so how do you know this works? Well, let's just highlight this notation, just run this bit of code right here, the name of our contingency table object, brackets, or in other words, matrix notation, and 1 comma nothing, okay? So 1 comma nothing, this is saying row 1, grab the data from row 1 of this table here, okay? If we just run that, you'll see that we've just grabbed the data there, so 90 and 70. And so when we nest this within the sum function from base R, we are saying just take the sum of 90 and 70 here, okay? And watch what happens if we just run this right here, just that chunk with sum and observed and row number 1 selected, we get 160. Now, back of the napkin, math here would tell us that 90 plus 70 is 160. So we did the right thing here, okay? Now I'm just going to run this whole line here because I want to make sure that I assign this value of 160 that I'm computing here to this new object I'm creating called N underscore men for the total sample size for men. If I run that, and you'll see over here, we get some verification that now in our global environment, we have this object we can reference again. You'll see 160L. L appears here because this is an integer, okay? That's a specific type of numeral. That's how you specify that in R if you'd like to do that. Okay, so now we're going to do the exact same thing, and we're going to do it for women. But all I'm going to do is I'm going to select and copy that line so that I can adapt that script. And I'm just going to change, instead of calling it N underscore men, I'm going to call this new object N underscore women. So I'm just adding a woe in front of men there, okay? And if we go back to the table we see in our console, instead of referencing the first row, which was for men who failed and passed, the total number, when you combine those, I'm going to reference the second row. So which what do you think I should change in this matrix notation here? Well, all I'm going to do is change 1 to a 2 here, okay? Because instead of referencing row 1, I'm now referencing row 2. So I'm computing the row marginal here for women, okay? Now, if I run that, you'll see the total number of women is 114, okay? That checks out here, 72 plus 42, 114. We're on the right track here. Okay, so the next thing that I'm going to do is I'm going to calculate the marginal, which is another way for saying the overall or total selection ratio, which is another way of saying selection rate, and just for the entire sample. So in other words, how many people pass this cognitive ability test? So that's the selection ratio, because presumably those people who pass this are then selected. You could also call this the pass rate if you wanted as well. But how many people pass this relative to the total sample size here, okay? So essentially what we're doing is we're saying the total selection ratio is going to be the sum of 70 over 42 divided by the total sum of all 4 of these values here, which would be 274, which we know from here is how many observations we have in this data set. So how can we do this? Well, first thing, like we did before, let's create a new object that we can subsequently reference, and we'll end up referencing this as well as these 2 objects here in the z-score, z-test formula that we're going to ultimately get to here. Well, the first object, let's call it SR underscore total. And this is just going to represent the overall total selection rate or selection ratio for our sample here with respect to this cognitive ability test, okay? So ignoring the gender distinction here, gender identity distinction, we're just going to focus on overall how many people passed relative to how many people took this cognitive ability test, okay? All right, so to the right of our left-handed arrow operator, this is where we're going to calculate that selection ratio that we'll subsequently assign to this new object called SR underscore total, okay? And so we are going to do the sum function again from base R, and again within the sum function parentheses as the sole parenthetical argument, we're going to start by referencing the observed contingency table object that we've created and referenced before, okay? And then we're going to add brackets once more. And now we're going to put our comma in. Remember, the value before the comma represents a row. Value after the comma represents a column here. And now let's put, instead of referencing a row, let's reference a column, okay? And I want to reference the total number, the column in which it contains the data or the number of people, the frequencies or counts of people who pass this cognitive ability test, okay? It's not column 1, which is right here under fail. It's column 2, which is under pass, okay? So this is the notation we use. Nothing, comma, 2, and we're referencing that column and the data, all the data contained across rows in that column there, okay? So we can verify this by just running that chunk there, and you'll see 112, okay? 70 plus 42 is 112, okay? So that checks out. That's the total number of people that pass. Now divided by, because this is a rate, okay, or a ratio, divided by the sum of observed, okay? The sum function, and then as a sole parenthetical argument, just put observed, okay? When you do this with the sum function and with a matrix or a table, what it's going to do, it's going to count up all values, numeric values, in this table, okay, or this matrix here. All right, so we have our observed object here, and so it's going to add up 90 plus 70 plus 72 plus 74. Let's verify that by just running that chunk. We should get 274. That checks out. That's our total sample size. Okay, so if we run this all together, it's going to assign our selection ratio or selection rate to this new object that's called capital S, capital R underscore total, all lowercase. Click run. Okay, we can just click on our SR underscore total object we just created there. And we see that our overall total selection rate is 0.408. So let's say 0.41. Okay, so 41% of the people in this sample that took the selection test, that is a cognitive ability test, they passed it. All right, so the next thing that we're going to do is we are going to convert our contingency table to proportions by row, okay? And so why are we doing this? This is so we can calculate more easily with our selection ratios specifically for men and specifically for women, okay? And there's different ways we could get to this, but this is the way that it's going to be a little bit more efficient. and it introduces a new function that you might find useful in other applications, okay? So I'm gonna create a new table object that I'm gonna call prop underscore observed. Somewhat arbitrary, but what I mean by this name that I'm creating here, you could call it something different if you'd like. This is gonna represent proportions observed, okay? So our observed proportions. And then do left-handed arrow operator here, so we can now assign our new table object values to this new object here called prop underscore observed. Okay, so what are we gonna do here? Well, we're gonna apply the prop.table function from base R. So prop.table, and as the first object, or first argument rather, provide the name of the contingency table object that we created up here. Okay, so we're using this as input. Now, as the second argument, we're going to enter the numeral 1. So why are we entering the numeral 1? Well, with this function, this prop.table function, if you put first, as the first argument, the name of the table. As a second argument, you are going to be putting either 1 or 2 here, and 1 indicates that you want to calculate the proportions by row, which in our case, if we calculate the proportions by row, it means that each row is going to add up to 1, where 1 would be 100%, okay? And so what that's going to give us is how many men, what proportion of men out of all men failed, what proportion out of all men passed. And it'll do the same thing for women. Okay, if we had put 2 here, it would do columns. So instead we'd be looking vertically here and we'd be saying, okay, where each column would add up to 1, the values would add up to 1 or 100%, it would be what proportion of people who failed were men and what proportion of people who failed were women, and so forth, and then over to the next column, okay? And so you'll get an idea if we just highlight this chunk of this code here, you'll see that this checks out, okay? So if you added up this row right here, for men, you'll see that if you add this up, the row marginal will be 1. Or 100% here, okay? So 0.56.25 plus 0.4375 adds up to 1.0, okay? So that checks out. Let's go ahead and run the whole thing so we can assign that to this new object that we're calling prop underscore observed that's gonna contain our proportions of our contingency table. Okay, so now using that, we are going to compute selection ratios, which as you've noticed so far, I've been abbreviating with SR, okay, for selection ratios. And again, sometimes you hear these referred to as selection rates, okay? So we've already calculated the overall selection ratio for the whole sample, or the pass rate, in other words. Now we're going to calculate the selection ratio specifically for men and the selection ratio specifically for women. And this would be the same thing that you would do in terms of the steps if you're running the 4/5 rule. Okay, so let's create our first object. We're going to do SR underscore min, okay, using a similar naming convention as we have up here with SR total. So selection rate for men, where S and R are capitalized. And we are going to reference that new object we created. Actually, I'll just copy it here to get the exact name so I don't make any spelling or transcription errors there. So prop underscore observed. And what I want to do is I just want to reference a specific cell now. So here's the table, that prop underscore table that I'm referencing right here. And I just want to reference for men, I just want to grab this value here. What is the proportion of men who passed this test? Okay. And so to reference this, I need to reference row number 1 and column number 2, because that's the value here. It's kind of like if you're familiar with the game Battleship, if you played that as a kid or as an adult. It's row number 1, you reference the row first and then column. So this is going to be 1, 2. So we'll use our bracket notation here, or not braces, but brackets. And we're going to put 1 for row 1, 2. Okay, and so let's verify this by just running that code chunk there. Okay, we see we get 0.4375. That's exactly the value we wanted to grab. And now let's run the whole thing so we can assign this to this new object called SR underscore men. All right, we've got that set up and we're just stockpiling these here. This is not the most, you don't necessarily need to do all these naming conventions, but I think for the sake of understanding what's happening behind the scenes, it's useful to understand what the basic math is here, or the basic arithmetic that we're applying here, as well as to understand some of the specific functions in a more isolated way. Okay, so let's copy this line here and then let's paste it below so we can do some adaptations. I'm just going to change this object name from SR underscore men to SR underscore women. So this will be the new object using a similar naming convention there. Still using the left-handed arrow because I'm going to assign a specific proportion, which is going to be the selection ratio for women here, okay? And the selection ratio for women is the proportion of people who passed out of all women, okay? Now, instead of referencing row number 1, we're now referencing row number 2 because that contains the data for the women. But we're still referencing column number 2 because that's the column that contains the the number of people who passed. And so now it's going to be using this matrix notation here, 2, 2. And let's verify it. It should grab 0.3684. So let's grab this chunk right here and just run it and see what we get in our console. Perfect. Grab the right value. Now let's run the whole thing and assign that value to this new object that we're calling SR underscore women. All right. Now we are finally ready to compute the z-test. Okay. And this, bear with me here, this formula is going to be a little bit longer than perhaps what you are maybe used to so far, or maybe you are used to longer formulas like this. And there's going to be a lot of parentheses in it, and so there's nesting within it. And so I'll try to make it as clear as possible and walk through each one of the steps here. Okay. Now I will pull up and show you the formula that we are going to be working on here. Okay, so we're going to start working on this formula here, which is for the z-test or the z-difference test here. And I just have a note here that this is really designed, and you'll see this in the formula. We're looking at the difference between our selection rate for our focal group, which is typically the protected class group that has the lower selection ratio, minus the selection rate for the referent group, which is the protected class group that has the higher selection ratio. So what the null hypothesis is for this z-test is that there's zero difference between the population selection ratios. So we find a significant z value, then we are going to reject this null hypothesis and conclude that there is a significant difference between the population selection ratios, okay? And so we'll get to the selection test in a little bit, but I'll show you how to both calculate a one-tailed and a two-tailed test here because there is some debate, or has been some debate over which is most appropriate and is it justifiable to use a one-tailed test in this specific context of assessing disparate or adverse impact, okay? And we'll get back to that in a second. Pull this over here. Okay. All right, so how do we compute the z-test? Well, let's do as we've done before, and let's create a variable or an object here that I'll call z, and this is a capital Z that I'm using here. I'm using the left-handed arrow here, and so I'm going to create a formula here to create our z-score or z-value that then we can test for its significance, okay? All right, so first we're going to start with the numerator here. Okay, and so you might remember this from the equation I just had on the screen there, and so I'll bring that to life using R notation here, okay? And so first we're going to take, in the numerator, it's just going to be the selection ratio of women minus the selection ratio for men. So we're going to take the selection ratio for our focal group, which happens to be women here, because they have this lower selection ratio, minus the selection ratio for men. Okay, so this is why I like doing it this way, where we're creating these separate objects, because it makes a little bit more sense. It's easier to read in the formula here. Okay, now this is our numerator, and so I'm going to put our division sign here, the /. And to make this easier to read, I'm going to go down to the next row, and that's typically how you'd read. Usually the numerator we'd position on the top and the denominator on the bottom. So everything I'm about to type in now is our denominator, okay? And so we're going to be taking the square root of multiple calculations that are on computations that will happen, and we'll take the square root of the value that comes out of those computations. Okay, so what I'm going to do is I'm going to split the parentheses up there. And just remember, we're taking the square root of everything here. And I'm splitting up the parentheses to hopefully make it easier to follow and easier to read here. Okay, so the first step that we're going to do is we're going to create a new set of parentheses here. And this is going to be the set of parentheses for a separate for our equations that go within the square root here. You don't necessarily need these, but I think it helps with the legibility here, okay? All right, so the first thing that I'm going to do is take our total. So I'm going to copy this value here, selection ratio for our total sample, okay? And times, so asterisk symbol is our times symbol. I'm adding another set of parentheses, our selection ratio total times 1 minus our selection ratio total, okay? And then I am going to do another multiplication sign right after these parentheses right here, after the 1 minus selection ratio total parentheses, times, I'm creating another set of parentheses here, 1 divided by the total number of women, okay? So this is the number of women in our focal group, plus 1 divided by the total number of men. So this is the total sample size of our referent group here, okay, our comparison group, if you will, okay? And so this is now the formula that we're going to be applying and taking the square root of all of this, okay? This essentially is getting at the standard error here for our test, okay? So here is where you're seeing really what our effect size is here, is just the difference between these two selection ratios is our numerator. And then as our indicator of standard error really comes in down here, okay? So this is really where we grab some of that information to come up with our test statistic here, which is our z-score in this context. Okay, so let's make sure that the parentheses all check out here. It's good to double check and make sure that all of them have a home here. Okay, so I think we are ready to go. Let's just highlight everything except the left-handed arrow and the z just to see what this value is. And it looks like I probably missed a parenthesis here. So let's see, we've got z, because that's not the value we should be looking for here. So z SR underscore total, and this gives you an idea how sometimes it gets challenging working with these formulas here. 1 minus times, oh, I see, this, and if you highlight the whole set here, so if I highlight this whole chunk here, so 1 over the number of women plus 1 divided by the total number of men, this should be one value here that we're multiplying here, okay? So this is what I mean about missing parentheses there. I thought something looked off there when I was counting these off. And so, in other words, I've put parentheses around this value here so we can multiply this whole sum here by the product of SR total times 1 minus SR total. Okay, let's try this again. Let's just run that chunk right there. Here we go. Okay, so now we're talking. This is our z-score here. Okay. And so now that looks like it's in a good position, let's go ahead and do the left-handed arrow in the whole chunk here so we can assign this negative 1.146 and some change z-score to this object that we're going to call a capital Z, okay? And so now it comes time for the significance test, okay? And so with what you need to remember in this context is this, okay? If the z value or the z-score, so this is our z value or z-score, I'll run it here again, negative 1.146. If the absolute value of that is less than 1.96, which is the cutoff or the critical score for a two-tailed distribution test or with an alpha equal to 0.05, we would conclude that there's no difference in these selection ratios. Okay, so we'd conclude that this difference of the selection ratio of women minus selection ratio of men, that there's no difference here, okay? And so here we do see that this absolute value of negative 1.146 is 1.146. That is less than 1.96. And so that gives us indication that, okay, we've met that threshold of statistical significance. This is the more conservative test here. It's a higher threshold when we have a two-tailed test here. Now, as I mentioned earlier, some people have argued that it's appropriate to use a one-tailed test in this specific context, which has become less conventional in statistics especially in the social sciences and so forth. And so the critical value for a one-tailed test is 1.65 or about 1.645. So I've just done some rounding there. And this one-tailed test, the alpha is still 0.05. We would find that this is also less than 1.65. It's less than this critical score. And so therefore, this is also evidence with this more liberal threshold here that we've also met the, we've also found that there is no statistical difference or no difference between the selection ratio for women minus the selection ratio for men here, okay? So we conclude that this would build evidence that there is not evidence of disparate impact or adverse impact here in this specific example, okay? Now, if our z-value, the absolute value of our z-value had been, let's say, 2.0, that would mean it would exceed this critical z-value here of 1.96, and at least with the two-tailed test here, we would say that this is not statistically, or this is a statistically significant difference because this value would exceed 1.96, okay? And if that were the case, then you would say, okay, we may have some evidence here that there's disparate impact or adverse impact happening with the cognitive ability test, at least with respect to men and women in terms of gender, okay? Where in this case, men are favored by this cognitive ability test in terms of their selection ratios, as we saw earlier, because they had the higher selection rate, okay? You can see over here, if you remember, the selection ratio for men is 0.4375, and for women, it was 0.3684, okay? But again, here, we conclude that there's no statistical difference between these two selection rates here. Now, what if you want to calculate the exact p-value for a one-tailed test with alpha equal to 0.05, okay? So instead of having to remember what this cutoff value is, if you find it easier to remember the following, then by all means, please do this. We have a function called p-norm, all lowercase in base R. Okay, if you type in p-norm, and then ABS, which stands for the absolute value, because we'll want to take the absolute value because this can be either a negative or positive value in terms of the z-score, and just copy and put into the sole, as a sole parenthetical argument in the ABS function from base R. Just put in z. If you just run this right here, just the ABS and the z argument within it, you'll see it's just taking the absolute value. So it just removes the negative sign if it's negative. If it's positive, it keeps it positive. Okay? So this is our first argument. So, comma, our second argument, we are going to write lower dot tail, okay? And this has to do with the distribution here, where the lower tail would refer to the low end here. So below the middle point of the distribution, and the upper tail would be the right hand of the distribution. In this case, we don't want the lower tail. We just want the upper tail here, okay? And for our one-tailed test there, we're saying this is the direction of it because we've taken the absolute value, so we're talking about a positive z-value here. So is this z-value right here, that's the absolute value of our z-value of 1.1464, is this significantly different from 0, is another way of thinking of this. Okay, if we run that, we get our one-tailed p-value, exact p-value of approximately 1.26, let's say. So if we know that our alpha level is 0.05, this is definitely greater than 0.05. And because it's greater than 0.05, we would fail to reject the null hypothesis that there is no difference in the means. Or in other words, we conclude we would just say there's no difference between these two selection ratios here, okay? No difference between these two selection ratios, at least statistically speaking. Now, what if you want a two-tailed test? Well, let's copy this, paste it below, and I'm just going to change this to two-tailed here. All we do is multiply this 2 times, I'll add some spaces here, maybe it's a little bit clearer. Oops. 2 times what we just used up here, p-norm, with our nested absolute value function with z, and then we're keeping lower dot tail. We still want the upper end, the right side of the tail of the distribution here. And if we do that, we get our p-value. That is 0.2516 approximately. So that is also obviously greater than alpha of 0.05. And so we would conclude here that this is not statistically significant. Again, this is just saying that we did not find evidence with this test of adverse or disparate impact when it comes to differences between men and women taking this particular cognitive ability test in this organization at this time. Okay, now here's something fun. So we just went through all these steps here. And if you watched my video on how you evaluate disparate impact or adverse impact using the 4/5 rule, chi-square test of independence, and the Fisher exact test, I cover the chi-square test of independence as I just mentioned. Okay, as it turns out, when you have a 2x2 contingency table that you're calculating a z-score for, and you have a 2x2 chi-square test of independence, you end up with a statistically equivalent chi-square test of independence. Okay, we're calculating a chi-square here, but what you'll see is the p-value will look really similar to the p-value for the two-tailed test that we just computed there. Okay, so how do we do this? Well, if you watch that other video, you'll know that the function is called chi-sq.test for chi-square test. So this is from base R. This is the name of our function, chisq.test. And then we simply put in as our first argument the name of that original object, which is our observed contingency table object here that had our original frequencies or counts, our observed frequencies. As our second argument, so after the comma, we are going to put in correct equals false. And the reason we're doing this is that by default, this function will apply with a 2x2 matrix, what's called the Yates continuity correction, which some people do use in this context for testing chi-square, or for testing for adverse impact or disparate impact. In our case, we're just going to run a conventional chi-square test, a Pearson chi-square. And to do so, we're just going to say correct equals false. We don't want that continuity correction. Okay, run this. All right. Here you get your chi-squared value. Degrees of freedom is going to be 1 because it's a 2x2 contingency table. Okay, 2 levels for each of the categorical variables. And we see that the p-value is 0.2516. If you round this right here for the p-value, the two-tailed p-value we just calculated, we see that it's 0.2516. This illustrates that in this particular context, with the 2x2 contingency table, a chi-square test of independence is going to be statistically equivalent to a z difference test that we just ran. Okay, so with all that said, it's really up to you. You can go through all these steps, and I think it's useful to learn how the z-test, which I should also mention up here, is also called the two standard deviation test. Okay, and the reason is that 2 standard deviations, the critical z-score for that is 1.96 approximately, and so that's why it's sometimes called colloquially the 2 standard deviation test. All right, but you could just run a chi-square test and know that the p-value will get you to the same place as far as a two-tailed test goes. All right, the next step is now we're ready to move on to the z impact ratio test, or the ZIR for short, Z sub IR. This is a test that's gained some favor. It can perform well in smaller samples, and so for that reason, some people like to use this test. And for another reason, so the effect size we were focusing on up here with the z-test was one selection ratio minus the other selection ratio. If you remember with the 4/5 rule, we're really interested in what's called the impact ratio, which is one selection ratio relative to another selection ratio, or in other words, one selection ratio divided by another selection ratio. And what the z-impact ratio test does is it keeps that effect size as the focus, okay? Because there is a difference if you're talking about the difference between two proportions or ratios, and the different and relative to the quotient between two ratios or proportions. And so we're going to work through the math here on how you can actually calculate the z-impact ratio, okay? So how do we do it in this context? Well, the first thing that we're going to do is we are going to create an object here. I'm going to call it capital Z underscore capital IR, and this is going to be our Z impact ratio that we can subsequently reference when we go to calculate the exact p-values and so forth. Okay, and so what is the formula here? Well, we're going to introduce the natural log, okay, so the natural logarithm, and we're going to be taking that the natural logarithm of our impact ratio, okay? And this is because this is an asymmetric distribution where one end will go to infinity, okay? So we're going to take the natural log, and the natural log function in R is just simply log, okay? And although you'll see natural log abbreviated as ln often, and so actually, which reminds me, we pull up the other formula here. Okay. And so this over here is what we're about to, this is the formula for we're about to calculate. So instead of log, you could also put ln, that's the other notation for the natural log of our impact ratio. So our impact ratio is just simply the ratio of our focal group, the selection ratio of our focal group, divided by the ratio of our referent group. So selection ratio of our women in this context divided by the selection ratio for men, okay? And then below, we're essentially getting at the standard error here for our actual ZIR, Z sub IR score that we're creating here. And that's going to help us with the statistical test, okay? All right, and I should note that the null hypothesis here, you can think of the null hypothesis as being that the population impact ratio, or IR, is 1. So if you divide one ratio by another and the resulting quotient value is 1.0, that means that they're equal, okay? So that's what we're testing here. The selection ratios are equal. So if we find a significant finding, it means we're rejecting this null hypothesis and therefore concluding that the selection ratios are not equal, okay? And we're going to have the same Z critical values and so forth, so we'll actually revisit those. All right, so we're first going to focus on, as the formula you just saw, we're going to focus on the numerator, and it's just going to be the log, or the natural log, of our impact ratio, where again, the impact ratio is simply, if we come up here, I'm just going to copy this so I can adapt it, copy the selection ratio of women and selection ratio of men, paste it here. See, try that again. Selection ratio of women and men. Paste that here. Okay, we're just going to change the minus sign, subtraction sign, to a division sign there. Just going to eliminate the spaces here. Okay, so this is our impact ratio here. So if we just ran this, we'd find that the impact ratio is 0.84. Sometimes this is called our adverse impact ratio in this context. And so what this is saying, this is where you would test this against the 4/5 rule or the 80% rule. Because this is greater than 0.80 or 4/5, we would conclude there's not evidence, according to that 4/5 rule, that there's prima facie evidence of adverse impact or disparate impact. If it had been less than that, then based on the 4/5 rule, we would conclude that there seems to be evidence of adverse impact. Although generally you shouldn't just stop with the 4/5 rule, you should also pair it with statistical tests like the Z impact ratio or Fisher's exact test or the chi-square test of independence. Okay, so here is our numerator right here, the natural log of our impact ratio, okay, divided by, and I'll go down to the next line here. We're going to be taking the square root again. And so I'm going to make this hopefully a little bit clearer by breaking up the parentheses there. And the first thing that we're going to do is we are going to take the 1 minus our total selection ratio for the sample. So remember, we actually used this up here, 1 minus the total selection ratio, okay? And we are going to divide that by the selection ratio, the total selection ratio just by itself, so not 1 minus it, okay? And then take that whole quotient there, so the value that comes out of this division here, put that in parentheses of their own, multiply that by, and here I'll make sure I get it right this time. In fact, you know what? I'm just going to grab, it's the exact same thing we were looking up at here with the Z test we looked at originally. It's the exact same. The other end of this product that we're going to be creating is just 1 over the total number of women plus the quotient of 1 over the total number of men here, okay? All right, and then we're going to take this whole thing here and we are going to put it in parentheses here, okay? Because we're going to take the square root of the value that comes out of this. So if we just ran this, the value is 0.0212. So let's see, when we run all this together, and I'm not going to use the left-handed arrow. I'm not going to select that and the name of our new object just yet because I just want to see what our z impact ratio is to make sure it's correct. Okay, that looks correct to me. So our z impact ratio score value is negative 1.6584. Okay, so let's go ahead and run the whole thing so we can assign that value to the object we're calling z underscore IR for z impact ratio. Okay, so I'm just gonna copy and paste this over because it's similar information as what I presented before, but do this more efficiently here. So in terms of statistical significance, if this value, the absolute value of our z impact ratio is less than 1.96, then we conclude that there's no difference between the selection ratios, okay? And really, there's no relative difference, I should say, because remember, we're basically saying that the impact ratio is no different than 1.0, which would mean that the two selection ratios are equal to each other, okay? Now, hypothetically, if this ZIR score had been greater than 1.96, like 2, then we would conclude that there is evidence, we would conclude that it is significantly different and that we do see that impact ratio seems to be deviating from 1.0. Okay, so in other words, the relative difference between the selection ratios is not 0. And this 1.96 value, it's the z critical value for a two-tailed test with alpha equal to 0.05. So that's the same as we saw before with the t-test or the z-test above. And the same goes for the one-tailed test. The critical value is still 1.65 or 1.645 if you want to be a little bit more precise. And we see in this case that still, even with the z impact ratio, even when we're changing the focus to looking at an effect size that's closer to the 4/5 rule, where we're actually looking at the impact ratio and whether it deviates from 1.0. In other words, whether there's any relative difference between these two selection ratios. And again, even with the one-tailed test, which is more liberal, we see that our z value is still, the absolute value is still less than this critical value of 1.65. So we would conclude that there doesn't seem to be a relative difference between these selection ratios. And so based on this test, we would again conclude that there doesn't seem to be evidence of adverse impact or disparate impact with respect to gender and this particular cognitive ability test in this company at this time, okay? So far, this has been a pretty clear case. This is not always going to happen. Sometimes these different these different statistical tests you might use, as well as the effect sizes you might calculate, might actually look a little bit different. They might have differing findings in terms of some might be statistically significant, some might be below or above a threshold, and so forth and so on, okay? Okay, so the next thing that I want to do is I'll just quickly show you're doing the same thing if you want to calculate the exact p-values for the z impact ratio. I'm just going to copy this from above where we did it for the z test, the z difference test up there. And the only thing I'm going to change here is I'm just going to copy the name of our new object, which is z underscore IR, and replace that with the other object name, which was just z. I'm replacing that in both of these equations here. So here, if you want to calculate the exact p-value for the one-tailed test, that's all we're changing. Same code as above. Now we see our p-value for the one-tailed test is 0.1218. That's still greater than our alpha level of 0.05, so we would still find that there's no significant difference here. Okay, at least statistically speaking. We can run the same thing with a two-tailed test. This is more conservative test, so not surprising that this is also not going to be significant because this p-value is greater than the alpha level of 0.05. Okay. All right. Now, one of the nice things about running the ZIR test, the Z impact ratio test, is that we can construct confidence intervals. Okay. And this can give you a little bit more idea of the sampling error that we're talking about, okay, when we're talking about these tests. And so by looking at kind of the width of the confidence interval that we end up with. Now, if you remember, we did the natural log that we ran up there, so we'll need to actually undo that with some exponentiation and Euler's number here in a little bit, sometimes called the anti-log transformation. And so what are we going to do? Well, first, in order to construct the confidence intervals, we are going to compute the natural log of the impact ratio. Okay, and we already did this above as part of this formula here. Okay, so I'm actually just going to copy that chunk there, because now we're just going to create an object out of it. And this object I'm going to call IR_log for just the natural logarithm or the logarithmic transformation of our impact ratio. Use the left-handed arrow operator. I'm just pasting, same thing we did before, just the log of our impact ratio, so selection ratio of women divided by selection ratio of men. Run that. I'm not even going to run this because it won't be super, well, actually I will. Here's the logarithmic transformation. Not very meaningful in and of itself. But now let's compute the standard error, because the standard error is we have to compute these in order to compute the confidence interval. Okay. So let's compute the standard error of the impact ratio, the IR. And so here's another formula for you. So it's going, let's call this object, we're going to create the capital S, capital E for standard error underscore IR, left-handed arrow. So we're going to assign the resulting value to this. And so we're going to start with the square root function here, sqrt from base R. And I'm going to split up the parentheses there to hopefully make this a little bit clearer. And the first thing we're going to do is 1 minus the selection ratio for women, which is our focal group here. And this is the name of the object we've referenced before, okay? And we are going to divide that. So within our square root, this is our numerator. Now we're going to do our denominator. Start a new line for that. And it is going to be the number of women, so the object we created that is in underscore women in our sample, times the selection ratio for women, so the object that we created for the selection ratio for women, plus, put in parentheses, 1 plus, or sorry, 1 minus the selection ratio for men. Okay. And divide that by the total number of men in our sample, n underscore men, times, times the selection ratio for men. Okay. And what I'm going to do next is I'm going to take this entire thing here, and just to make this clear, I'm going to put the first parentheses to surround this whole thing by an extra set of parentheses to show that this whole set of computations here, we're taking the square root of this. Okay. All right. And then that's going to be our standard error for impact ratio, which we'll use to compute the confidence interval. Let's run that. Let's take a look at this object we created and the value that's been assigned to it, the standard error of the impact ratio. It's 0.1518. Okay, good. Now we're ready to create or compute the bounds of our confidence interval. Okay. And this is going to be a 95% confidence interval. I should be specific there. Now we're going to create the lower confidence limit, and specifically we're going to be creating, this is going to be the lower confidence limit and the log of it, because we're still in this, since we used the log transformation here above in terms of our impact ratio log, and that's going to be used to compute this initial lower confidence limit. We're going to call this LCL, lower confidence limit underscore log, just to remind ourselves that this object we're creating is going to have be a logarithmic transformation, natural log. And so you could call this whatever you want. I'm calling it that, and we call it whatever we want because it comes to the left-hand side of the arrow operator there. And now we're going to reference the natural log of our impact ratio we created there, that object, IR underscore log. And the lower limit is going to be 1 minus 1.96. Okay, this value should look a little familiar here. This is a two-tailed test there. Okay, times our standard error. Okay, so times our standard error here. And I'll make a little notation to the left here that this is our lower confidence limit. Okay, and so if you run this, and then run just the LCL log to see what that value is. So this is our lower confidence limit is here, but this is still the logarithmic transformation, okay? We haven't exponentiated it yet to get it back to the same metric as our original impact ratio, okay? All right, so let's do the same thing with the upper confidence limit. So we'll copy that, paste, and I'm just going to change LCL to UCL for upper confidence limit. And instead, the only other thing I'm going to change here is instead of minus 1.96, it's plus 1.96 because this is our upper limit. And I'm just going to change the note here to reflect the upper confidence limit. Let's run that line. See our work by running the new object, UCL underscore log. Okay, and here's the logarithmic transformation of that upper confidence limit. So how do we get these confidence limits, our upper and lower limits, to the same metric as our original impact ratio? Well, we're going to exponentiate them, okay? So I'll make a note here, we're going to convert to the scale of the original impact ratio metric, okay? And so I'm going to create two new objects here. LCL just means good old-fashioned lower confidence limit. In this context, it's going to be in the scale of the original impact ratio. Okay, and if you remember, the impact ratio value we're talking about here is again 0.842. Okay, so all we're going to use is the exp function from base R. And this is an exponential function, so we're exponentiating here. This is going to do what's sometimes called an anti-log, okay? And we're just going to copy the LCL log, so the lower confidence limit, the logarithmic transformation of that, paste it as our sole parenthetical argument here. Okay, copy that because I just want to tweak that in the line below here. And I'm just going to change LCL to UCL, so the new object will be UCL. And now I'm just going to copy the UCL underscore log object here, and we're going to exponentiate that as well. Run both of those. And now let's just run each of these to see the upper and lower confidence limit. Okay, so the upper and lower confidence limit of our impact ratio is 0.62 to 1.13. Okay. Remember, if our impact ratio is equal to 1, it means the proportions are the same. The selection ratios are the same. We're not seeing evidence of any bias. Okay. Now notice our 95% upper and lower confidence limit includes that 1.0 value. Well, this is telling us here that this is not a significant finding. It's telling us the same thing that our p-values told us above. But this gives us a little bit of an idea of what the bounds of our confidence interval, how wide they are here. Okay, and you can see this is fairly wide. And so you would interpret this, because this is a 95% confidence interval, you would interpret this that we can be essentially 95% confident that our true impact ratio is captured within this interval, okay? Or that this interval captures our true impact ratio is somewhere between 0.625 and 1.134, okay? So 95% confidence in that statement. All right, so this is, again, one of the advantages of doing the z-impact ratio is creating these confidence intervals here. Gives you a little bit more idea of the sampling error that you're working with. And hopefully this elucidates this process of actually calculating the z-impact ratio, which there's been quite a bit written about it. I'm not, in terms of practice, because this is a more complicated test to actually estimate and implement, I do get the impression that fewer people actually use this, but this is a viable test that you might use in certain circumstances. And again, I turn you back to the beginning of this tutorial where I gave you some recommended readings. You can learn more about the different types of, specifically the statistical test, and again, simulation work that's been done regarding their power and type 1, type 2 errors, or false positive, false negatives, as well as how they perform in different size samples and when you have selection ratios that are at different extremes and so forth, okay? So this wraps up the tutorial on how to evaluate disparate or adverse impact using the z-test, sometimes called the z-difference test, and the z-impact ratio test. As I've mentioned several times in this video, if you're interested in learning how to calculate the 4/5 rule, the chi-square test of independence with and without Yates continuity correction, and Finch's the exact test, then I would recommend checking out an additional video tutorial that I've created on this topic. And I'll put the link to that in the description of this video.